We're going to be talking about force today, specifically what force is, the different types of forces, and how do we identify and represent forces that are acting on an object. So what is force? In the most general terms, force is a push or a pull. Forces can cause changes in motion. So that's the biggest thing here. It's not that force just causes motion, because an object that has no net force acting on it can actually be in motion at a constant speed. But forces will cause changes in motion. The SI unit for force is the Newton, and 1 Newton equals 1 kilogram times 1 meter per second squared. There are two different main types of forces. There are contact forces and field forces. Contact forces involve any time the two objects have to be in contact with one another for the force to be exerted. These include frictional force, tension force, normal force, air resistance force, applied force, and spring force. Field forces, sometimes called distance forces or at a distance forces, are any object that don't have to come in contact with one another to experience the force. So for example, gravitational force, if you and the Earth do not have to be in contact with one another for you to feel the effects of gravity. When you jump into the air, the Earth will still pull you back towards its center, even though you don't have to be in contact with one another. The same thing with electrical force and magnetic force, which are often combined to be called the electromagnetic force. We're going to go through each of these forces very briefly. We're going to talk about what is the annotation that we use on a force diagram. So for example, applied force is F sub A, with the subscript A. So that's a force that's applied to an object by a person or another object. So this person pushing the elephant is giving an applied force. If the elephant was pushing another elephant, or the elephant was pushing a block, anytime the two objects come in contact with another to apply a force, we just call this a general applied force. Next is frictional force. We're going to talk a little bit more about the different types of frictional forces, but in general, the frictional force is a force exerted by a surface as the object moves across it and makes an effort to move across it. We have to make that distinction there, makes an effort to move across it, because sometimes if you're trying to push an object that's very heavy and it's not moving, that's because the frictional force is causing the object not to move. So even though you're making an effort to move it, the object isn't moving due to frictional force. Or when you are sliding an object, frictional force always acts in the direction opposite of motion. Tension force. Tension force is F sub T, and it's transmitted through strings, ropes, wires, etc. when pulled tight by forces acting on opposite ends. The tension is always equal and opposite. So the tension in the cord pulled by the man in the green shirt is the same as the tension in the cord by the woman pulled by in the purple shirt. Same cord, same tension. Normal force. Normal force is the support force exerted by an object that is in contact with another stable object. The normal force always acts perpendicularly to the surface of the object. So let's pay attention to this one, because we're going to see a lot of the normal force this year, or in this chapter at least. So the forces are always equal and opposite, so they don't slide down at the top here. So you can see that the force of gravity is pulling down, but the normal force, when they're on the flat part of the surface up here, is pointing straight upward. However, as they start to slide down the surface, the force of gravity always pulls straight down towards the center of the Earth, but the normal force is perpendicular to the surface. In this case, we would have to think about the components of the normal force, and the person is going to be able to accelerate down the slide, but we'll talk more about that later. So for now, just remember that the normal force is the support force exerted by a stable object, so anytime an object is resting on a stable surface, and it always acts perpendicular to the surface. Air resistance force. Now, often here in Happy Physics Land, as I call it, we neglect air resistance, but unless it's specifically stated, you should generally not neglect the air resistance, or you should label it on a force diagram. So in this case, it's clear that the person is experiencing air resistance with his parachute filled with air. So air, this acts on objects as they travel through the air. Air resistance is technically a type of frictional force. We call it fluid friction. So just like any other friction force, it opposes the motion. So again, we see gravity pulling straight down, and the air resistance would oppose the motion. Spring force, the force exerted by a compressed or stretched spring upon any object that's attached to it. So if I pull this object down, say I pulled it down to here, and the spring was stretched out, it would be pulling the object up. However, if I push this block upward and now the spring is very compressed, it's going to push the object downward. So we'll have to think about whether the spring is stretched or compressed when we're talking about the direction of the spring force. And gravitational force. This is going to exist on every object that we draw, so it's important that we draw it correctly. So the force with which the Earth, Moon, or any other massively large object attracts another object towards itself. Another word for the gravitational force is the weight of an object. So we say that weight is equal to mass times the acceleration due to gravity. It's very important to note that weight is not the same as mass. Mass is about the amount of matter that you are made up of, whereas weight is affected by gravity. Your weight will change if you went to the moon because the acceleration due to gravity on the moon is much less than it is here on Earth. So this g is that value of 10 meters per second squared that we've been using throughout this year. Gravitational force is always directed downward towards the center of the Earth. So make sure we're always drawing our gravitational force straight downward. Now some of these other field forces, the electrical force and the magnetic force, it's often referred to as the electromagnetic force. So this is what keeps charged particles in an atom together. So we have the protons in the nucleus and the electrons surrounding the nucleus are held together by these electrical forces of opposite charges. And like I said, they're often grouped together as the electromagnetic force. Okay, so what we're going to focus on now, we have our whole list of different forces that we're able to work with, and so we are going to be drawing force diagrams or free body diagrams for different objects in various scenarios. So place the origin of the axis at the center of the object. So as you saw in the Ed puzzle, generally you can draw an outline of the object if you'd like, but all forces generally originate from the center of mass of the object. So more often I tend to draw just a dot to represent the object's center of mass, and then all forces can come from that dot. Orient the axis so it's angled in the direction of motion. So I'd like to know exactly where is the object moving so that I have an idea of where the different forces will be acting. And then draw force vectors radiating from the origin in their appropriate directions. All right, so we're going to do a bunch of examples here of drawing force diagrams, and then you'll be trying some on your own in the Khan Academy assignment. So starting out more simply, so draw a force diagram for the apple which is being pushed across the table by an ant. So I'm going to draw force diagrams here. So first, I'm going to draw it up in here on the side so that we can see it a little better. This dot represents the center of mass of the apple. All right, so let's think about the forces acting on the ants, or on the apple, sorry. So first of all, we know that the force of gravity always acts straight downward. So I draw a downward vector, and I always make sure to label it force of gravity. These are technically vectors, so you can put the vector symbol over it if you'd like. I'm going to leave them off for now. All right, now, another force, what I want to think about, does the normal force exist? It doesn't always. So think, is this apple resting on a stable surface? It's resting on the table, which is a stable surface, so I know that the table is pushing back up with the normal force, so F sub n. Okay, so now the ant is pushing it across. We're just going to call that an applied force. So F applied. And now, generally, it'll say if this is a rough surface, it doesn't say to neglect friction, so we can't just ignore it. And you can see this ant is struggling. So there must be some friction on the surface. So this will be the force of friction, which is always opposing the motion or the attempted motion of the object. So this is a force diagram of our apple being pushed across the table by an ant. All right, so let's look at some more examples. So I'm going to draw a force diagram for the apple resting on the scaffolding. And then I'm going to draw a force diagram for the scaffolding. Okay, so we're going to do two separate diagrams. The first one's going to be for the apple. And the second one is going to be for the scaffolding. Oops. just going to scaffold. All right, so for the apple, here's my dot representing the center of mass, right here in the middle of the apple. So this is pretty straightforward. So the apple has force of gravity pulling down, and the apple's resting on this stable surface, so it's going to have the normal force pushing up. All right. So now the scaffolding. So again, the center of mass of the scaffolding. So we'll just draw a dot. Now the scaffolding has two different wires pulling up on it. But we're not going to draw them off to the side. We're just going to put them basically right next to each other. So we're going to call it force of tension 1. And I'm going to draw a second arrow here. Force of tension 2. Sorry, it's supposed to be coming off of the dot, but it's hard on the iPad. All right. We also have the force of gravity pulling down on the scaffolding, so that's the weight of the scaffolding, but you also have the force of the apple pushing down on the scaffolding as well. So we're going to call that the force of gravity of the scaffolding and the gravity from the apple, which often is referred to as a normal force from the apple. So you can think there are 4 forces acting on the scaffolding, but only 2 forces acting on the apple. So when you're drawing force diagrams, it's really important to think about which object are we actually talking about. We didn't draw all of the ropes attached to the apple because the ropes are actually attached to the scaffolding. So pay attention to which object you're being asked to draw force diagrams for. Okay, a force diagram for an apple which is sliding down a rough ramp. So here I have my dot. Now this is a good example of when it's sometimes helpful to think about what is the direction of motion. So the object's sliding down. So you guys can see I'm going to draw just like a dotted line here for my axis. And I know the object's moving down this way in the x direction. Okay, so when we tilt an axis like this, sometimes it can be tricky to identify which way is the object moving. So I can label my x and y axes and know it's sliding along the x-axis. This is just going to help me draw my force vectors correctly. Now, force of gravity still always pulls straight down, even though the object's on a slanted surface. But this time, the normal force is going to be perpendicular to the surface. So instead of going straight up, it's going to go perpendicular to the surface, which I drew as a dotted line. I also know it's sliding down a rough ramp, so that means that the force of friction is acting between the apple and the ramp. So it's going to go along this axis, the force of friction. Okay, it's important to note that there's no applied force going down the ramp. The component of gravity that acts in the x direction, you can see that gravity falls between the x-axis and the y-axis here. So part of this force of gravity is actually acting in this x direction that's going to cause the apple to slide down the ramp. Nothing is pushing the apple down the ramp with an applied force. Okay, an apple is suspended by 2 strings. So here we go. So this one's pretty straightforward. We always have the force of gravity pulling down. And now we're going to draw these tension forces because these are wires, so they're going to have tension force in them. I'm going to draw them exactly as I would see coming from the apple. So the first one would be this way, force of tension 1, and the other one this way, force of tension 2. There's no normal force here because there's no stable surface that the object's resting on. Instead, the support is being provided by the tension. All right, and then an apple falling out of a tree. So if this apple was in free fall, or if I said to neglect air resistance, the only force that would be acting on the apple would be the force of gravity. However, if it doesn't say to neglect air resistance, we're also going to say that the force of air resistance is acting in a direction opposing motion on the apple. So pay attention to whether or not you're being told to neglect air resistance or to include it. Okay, so hopefully this gave you a good range of ideas about how we draw force diagrams, so the different types of forces we'll encounter. So we'll be doing some more practice with this in the upcoming week. So try some out on the Khan Academy and let me know if you have any questions.